right now, above your head, there are roughly 200 billion trillion stars burning in the observable universe. That number is so large that if you tried to count them, one per second, it would take you over 6 trillion years just to finish. Stars are everywhere. They fill galaxies like grains of sand on an infinite beach. They cluster in enormous groups. They drift alone through the voids between cosmic structures. They orbit each other in binary pairs and triple systems. And they whirl in gravitational dances. We are so surrounded by starlight, so immersed in it, that we have never known a universe without it. But here is a fact that should stop you cold. There was a time, not at the beginning of the universe, but hundreds of millions of years after it began, when there were no stars at all, not a single one, anywhere. The cosmos was dark, not in the way a room is dark when you turn off the lights, where you can still sense the walls and feel the furniture, and know that dawn is coming, not in the way the deep ocean is dark, where at least bioluminescent creatures flicker in the abyss. No, the universe was dark in an absolute, total, all-encompassing way that is almost impossible for the human mind to truly comprehend. No pinpricks of light anywhere. No distant galaxies glowing in soft spirals. No nebulae shimmering in curtains of gas and dust. Nothing but a vast, cooling, expanding ocean of hydrogen and helium, stretching in every direction for billions of light years, utterly featureless, utterly silent, utterly black. This period is known as the Cosmic Dark Ages, and it lasted for hundreds of millions of years. And then, something changed. Deep within invisible structures of dark matter, inside clouds of primordial gas that had been slowly, patiently, relentlessly gathering under the pull of gravity for eons, temperatures and pressures rose to a breaking point. Hydrogen nuclei, stripped bare, moving at incredible speeds, began slamming into each other with enough force to fuse. Energy erupted outward. Light, real light, the first photons produced by a star since the universe became transparent, burst into existence in a cosmos that had never seen anything like it. The first star ignited, and the eternal night began to shatter. This is the story of how that happened. How the universe went from perfect, featureless darkness to the blazing, star-filled cosmos we inhabit today. It is a story of gravity and patience, of chemistry and violence, of stars so enormous and so powerful that nothing like them exists anymore. Not anywhere in the observable universe. It is a story that connects the hydrogen atoms forged in the first 3 minutes after the Big Bang to the iron in your blood, and the calcium in your bones, and the oxygen in your lungs. It is, in every meaningful sense, the story of how the lights came on, and how those lights made everything that followed, including you and me, possible. So settle in. Get comfortable. We are going all the way back past the formation of our solar system, past the birth of the Milky Way, past the earliest galaxies, past the first flickers of starlight, all the way back to a time before there was anything to see at all. And from there, slowly and carefully, we will watch as the universe builds its first fires from nothing but gravity, gas, and an almost unimaginable amount of time. To understand how the first stars were born, you have to understand what came before them. And what came before them was, in a word, everything. Everything that exists. Everything that has ever existed. Every single particle of matter. Every photon of light. Every joule of energy in the entire observable universe. All of it, every last bit, traces back to a single event approximately 13.8 billion years ago, the Big Bang. Now, the Big Bang is one of those phrases that has been so widely used in so many science fiction movies and popular articles and late-night conversations that it has almost lost its meaning. People imagine an explosion, a bomb going off somewhere in empty space, debris and shrapnel flying outward in all directions. But that is not what happened. Not even close. There was no empty space for an explosion to occur in, because there was no space at all. Space did not exist before the Big Bang. The Big Bang was not an explosion in space. It was an explosion of space. Space itself, along with time, matter, energy, and the very laws of physics, erupted into existence in an event that defies human intuition at every turn. In the first unimaginably tiny fraction of a second, fractions so small that we have to use scientific notation just to write them down. Conditions were so extreme that the laws of physics, as we understand them, had not yet fully separated from one another. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single superforce. Temperatures were in the trillions upon trillions of degrees. Densities were beyond anything we can meaningfully describe. The universe was a seething, roiling quantum foam, a state of matter so exotic that we do not fully understand it even now. But the universe was expanding faster than light, in fact, during the brief period known as cosmic inflation, a burst of exponential growth that took the universe from something smaller than an atom to something larger than the observable universe in less than a trillionth of a second. Inflation smoothed out the early universe, flattening its geometry and spreading its energy almost, but not quite, perfectly evenly across space. Those not quite imperfections, quantum fluctuations frozen into the fabric of space by the rapid expansion, would turn out to be among the most important features in all of cosmic history. But their time had not yet come. They would lie dormant for hundreds of millions of years. As the universe expanded and cooled in the moments after inflation ended, the fundamental forces separated from one another. Quarks, the building blocks of protons and neutrons, condensed out of the primordial energy. Within the first millionth of a second, the universe had cooled enough for quarks to bind together into protons and neutrons, the familiar particles of atomic nuclei. Electrons buzzed everywhere, too energetic to be captured by any nucleus. Photons ricocheted off everything. The universe was a dense, blinding, white-hot fog. Within the first second, the temperature dropped to about 10 billion degrees. Neutrinos, the ghostly particles that barely interact with matter at all, decoupled from everything else and began streaming freely through space. They are still streaming today, right now, an invisible sea of primordial neutrinos left over from the first second of the universe. Roughly 65 billion of them pass through every square centimeter of your body every single second, and you feel absolutely nothing. And then, starting at about 10 seconds after the Big Bang, and continuing for roughly the next 20 minutes, something extraordinary happened. The universe became a nuclear reactor. This brief window of time is known as Big Bang nucleosynthesis, and it is one of the most important events in all of cosmic history. the temperature of the universe, still hundreds of millions of degrees, was just right for nuclear fusion to occur. Protons and neutrons began smashing together and sticking. First, they formed deuterium, a heavy isotope of hydrogen consisting of one proton and one neutron. Deuterium is fragile, easily broken apart by high-energy photons. And for the first few minutes, as fast as deuterium formed, it was destroyed. This is called the deuterium bottleneck, and it delayed the whole process until the universe cooled enough for deuterium to survive. Once that bottleneck cleared, fusion proceeded rapidly. Deuterium nuclei fused with protons to create helium-3. Helium-3 nuclei combined to produce helium-4, the common form of helium, with 2 protons and 2 neutrons locked together by the strong nuclear force. Nearly every available neutron was incorporated into helium-4. Because helium-4 has one of the highest binding energies per nucleon of any light nucleus, it is a remarkably stable configuration, a fact that would have enormous consequences for the chemistry of the early universe. A tiny, almost negligible amount of lithium was produced as well. Lithium-7, with 3 protons and 4 neutrons, is the heaviest element the Big Bang could manage. The reason heavier elements could not form is fascinating. There is no stable nucleus with 5 or 8 nucleons. This means that when you try to add a proton or neutron to helium-4 to make a nucleus of mass 5, it falls apart almost instantly. And when you try to fuse 2 helium-4 nuclei to make beryllium-8, it is equally unstable. The Big Bang hit a wall. Without stable stepping stones to bridge the gap between helium and heavier elements, nucleosynthesis ground to a halt. And then the window closed. The universe had expanded and cooled too much for fusion to continue. By the time the universe was about 20 minutes old, its chemical composition was permanently set. Roughly 75% hydrogen by mass, 25% helium, a trace of deuterium and helium-3, an almost vanishingly small amount of lithium. And that was it. That was the entire periodic table of the newborn universe. Hydrogen, helium, and a whisper of lithium. No carbon, no oxygen, no nitrogen, no iron, no silicon, no gold, no silver, no phosphorus, no sulfur, no chlorine. None of the 92 naturally occurring elements that make up the Earth, that compose the oceans and the atmosphere, that build the intricate molecular machinery of every living cell. Those elements simply were not there. The Big Bang could not make them. The mass 5 and mass 8 gaps in nuclear stability blocked the path to anything heavier, and the window of suitable temperature closed before any workaround could be found. This is worth dwelling on because its implications are staggering. For the first few 100 million years of its existence, the universe was chemically simple to an almost absurd degree. 3 elements. That is all. No complex chemistry was possible. No molecules more complicated than molecular hydrogen and the occasional lithium hydride. No solid matter of any kind. No dust, no minerals, no crystals, no rocks. The entire observable universe was a gas of hydrogen and helium, and nothing else, expanding and cooling in the dark. The rich chemical complexity we see around us, the 100+ elements of the periodic table, the millions of known chemical compounds, the breathtaking molecular intricacy of DNA and proteins, and chlorophyll and hemoglobin. All of it had to be built from scratch, built atom by atom, element by element, inside the nuclear furnaces of stars that had not yet been born. The universe's chemical history had to start from almost nothing and work its way up over billions of years to the staggering diversity of matter we see today. And that process began with a single step, the birth of the first star. But we are getting ahead of ourselves. For now, the universe was a hot, dense, expanding soup of hydrogen and helium nuclei, free electrons and photons, and those photons were trapped. Because the universe was still a plasma, meaning electrons were too energetic to be captured by nuclei and floated free in the gas. Every photon that tried to travel in a straight line would almost immediately collide with a free electron and get scattered in a random direction. The universe was opaque. Light could not travel through it in any meaningful way. The mean free path of a photon, the average distance it could travel before hitting an electron, was minuscule. If you could somehow have existed at that time and opened your eyes, you would have seen nothing recognizable. Not darkness, not distinct light, just a brilliant, featureless, white-hot glow in every direction, like being inside a furnace. This state of affairs continued for a very long time by human standards, though a relatively short time by cosmic ones. For roughly 380,000 years after the Big Bang, the universe remained in this plasma state, hot, opaque, filled with light that could not travel anywhere. But the universe was still expanding, still cooling. And eventually, the temperature dropped below a critical threshold, about 3,000 degrees Kelvin, roughly the temperature of the surface of a cool red dwarf star. At that temperature, something beautiful happened. Electrons slowed down enough to be captured by hydrogen and helium nuclei. For the first time in the history of the universe, neutral atoms formed, hydrogen atoms, each with one proton and one electron. Helium atoms, each with two protons, two neutrons, and two electrons orbiting the nucleus. This event is called recombination, which is something of a misnomer because these protons and electrons had never actually been combined before. It was their first union, not a reunion. But the name has stuck. The consequences were immediate and profound. With the free electrons now bound inside atoms, photons suddenly had nothing to scatter off. The fog cleared. In a cosmic instant, the universe went from opaque to transparent. Light was free. Photons that had been bouncing uselessly between electrons for hundreds of thousands of years suddenly found themselves with a clear path. They streaked outward in every direction, carrying with them a snapshot of the universe at that exact moment. A snapshot of a cosmos that was almost perfectly uniform, but contained those tiny, tiny density fluctuations planted by inflation. Variations of just one part in 100,000. Those photons are still traveling today. They have been stretched by 13.8 billion years of cosmic expansion, from visible light to microwave radiation, cooled from 3,000 degrees to just 2.725 degrees above absolute zero. We call them the cosmic microwave background, and they are the oldest light in the universe. When scientists at Bell Labs, Arno Penzias, and Robert Wilson accidentally discovered this radiation in 1965 while trying to calibrate a radio antenna, They had no idea they were listening to the afterglow of the Big Bang itself. They initially thought the persistent hiss in their detector was caused by pigeon droppings on the antenna. They cleaned off the droppings. The hiss remained. It was coming from the entire sky. It was coming from the beginning of time. They would win the Nobel Prize for their discovery in 1978, sharing it with the cosmic microwave background that refused to be silenced. Subsequent satellite missions mapped the CMB with ever-increasing precision. NASA's Cosmic Background Explorer, or COBE, launched in 1989, was the first to confirm that the CMB had a perfect blackbody spectrum, exactly the radiation profile predicted for the cooling fireball of the Big Bang. COBE also made the first detection of the tiny temperature fluctuations in the CMB. Those 1 in 100,000 variations that represented the seeds of all future cosmic structure. When the COBE team presented their results at a meeting of the American Astronomical Society in 1992, the cosmologist George Smoot described the CMB fluctuation map as being like looking at the face of God. It was the most precise confirmation of the Big Bang theory ever obtained. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched by NASA in 2001, sharpened the picture dramatically, measuring the fluctuations with enough detail to determine the age of the universe, its geometry, the proportions of ordinary matter, and dark energy, and the rate at which it was expanding. And the European Space Agency's Planck satellite, launched in 2009, pushed the precision even further, producing the most detailed all-sky map of the CMB that we possess today. Planck's measurements constrained cosmological parameters to percent-level accuracy and provided crucial evidence about the timing and duration of reionization. By measuring the polarization of CMB photons that had scattered off the free electrons produced when the first stars ionized the intergalactic medium, the cosmic microwave background is, without exaggeration, the single most important observational tool in all of cosmology. It is the foundation upon which our entire understanding of the Big Bang, the structure of the universe, and the origin of cosmic structures is built. And yet, despite its brilliance as a scientific tool, its release also marked a beginning. The beginning of darkness. In the decades that followed, increasingly sophisticated instruments were aimed at this ancient radiation. The COBE satellite, launched in 1989, made the first precise measurement of the CMB spectrum and confirmed that it was an almost perfect blackbody, radiation in thermal equilibrium, exactly as predicted by Big Bang theory. More importantly, COBE detected, for the very first time, the tiny temperature fluctuations superimposed on the smooth background. The announcement in 1992 was front-page news around the world. The physicist George Smoot, who led the COBE analysis, described the fluctuation map as looking at the face of God. It was a poetic exaggeration, but the sentiment was understandable. For the first time, humanity was looking at the oldest structures in the universe, the seeds from which everything we know would grow. Later missions refined the picture further. The WMAP satellite, launched in 2001, mapped the fluctuations with much greater precision, constraining the age, geometry, and composition of the universe with remarkable accuracy. And the Planck satellite, launched by the European Space Agency in 2009, produced the most detailed all-sky map of the CMB to date, measuring temperature variations down to millionths of a degree across the entire celestial sphere. Each generation of observations confirmed and refined the same picture: a universe that is flat in geometry, dominated by dark energy and dark matter, with just a small percentage of ordinary baryonic matter, and seeded with small density fluctuations that are consistent with having been generated during cosmic inflation. Those fluctuations, those regions where the radiation is slightly warmer or slightly cooler than average by millionths of a degree, correspond to regions where matter was ever so slightly denser or slightly less dense than average at the time of recombination. And those fluctuations are the seeds of everything. Every galaxy, every star, every planet, every ocean, every mountain, every tree, every bacterium, every person reading these words, all of it traces its origin to those minuscule density variations in the cosmic microwave background. They are the blueprints of the cosmos, written in the faintest possible ink, stamped onto the very fabric of the universe at its dawn. With recombination complete, with the universe now clear and cooling, with those subtle density variations quietly imprinted in the distribution of matter, the stage was set for the longest, darkest, most silent chapter in cosmic history. The cosmic dark ages had begun. Imagine darkness, not the darkness of a moonless night, where you can still see the faint glow of the Milky Way arching overhead like a river of spilled milk, and the dim outlines of the horizon against the sky. Not the darkness of a deep cave, where at least you know that somewhere above you there is a surface with sunlight streaming across it and birds singing. Not the darkness of a power outage, where you fumble for a flashlight and wait for the electricity to return. Imagine instead a darkness that extends in every direction for billions of light years with absolutely nothing to interrupt it. No stars, no galaxies, no nebulae, no auroras, no lightning, no bioluminescence. Nothing. The cosmic microwave background radiation was still present, still filling all of space. But within a few million years of recombination, it had redshifted out of the visible spectrum entirely, stretching from visible light through the infrared and into the microwave. From that point forward, the universe contained no visible light whatsoever. None. If you could somehow teleport yourself into this era and open your eyes, you would see absolutely nothing. Not a faint glow in the distance, not a shimmer on the horizon. Perfect, total, infinite blackness, extending in every direction for as far as the universe reached. This is the cosmic dark ages. They lasted from roughly 380,000 years after the Big Bang until somewhere between 100 million and perhaps 200 million years later, when the very first stars began to form. In human terms, those numbers are staggeringly large. The Dark Ages lasted longer than our entire species has existed, longer than most species on Earth have existed, longer than the entire age of the dinosaurs, longer than the time it has taken for the continents to drift from the supercontinent Pangaea to their current positions. The universe spent an almost incomprehensible span of time in total, complete, unbroken darkness. Think of it this way. If you compressed the entire history of the universe into a single calendar year, with the Big Bang occurring at midnight on January 1st, and the present day falling at midnight on December 31st. The cosmic dark ages would last from the early hours of January 1st until roughly January 10th, more than a week of cosmic silence. In a calendar where all of recorded human history occupies the last fraction of a second before midnight on December 31st. During these millions of years, the temperature of the universe dropped steadily as space continued to expand. At the beginning of the Dark Ages, the temperature was about 3,000 Kelvin. By the time the first stars formed, it had fallen to roughly 60 Kelvin, about minus 213 degrees Celsius. The universe was cold, dark, and nearly featureless. Almost, not quite, because the Dark Ages were not a period of nothing happening. Beneath that all-consuming darkness, forces were at work that would reshape the cosmos. The historian's analogy is apt, just as the so-called Dark Ages of European history, from roughly the 5th to the 10th century, were not actually a period of intellectual stagnation, but a time of quiet transformation that set the stage for the Renaissance. The cosmic Dark Ages were a time of hidden change, of structures forming in the shadows, of gravitational forces slowly assembling the architecture that would support the first lights when they finally appeared. Gravity, the weakest of the four fundamental forces, but the only one that operates effectively over truly enormous distances, was slowly, patiently, relentlessly pulling matter together, and the structures it was building were extraordinary in their scale and intricacy. Remember those tiny fluctuations in the cosmic microwave background. Those regions where matter was just slightly denser than the average, by perhaps 1 part in 100,000. Gravity seized upon those overdensities and began to amplify them. Where there was a little more matter, there was a little more gravitational pull. That slightly stronger pull attracted a little more matter from the surrounding regions. The additional matter increased the gravitational pull further, which attracted still more matter. It was a feedback loop, positive reinforcement operating on the grandest possible scale, exquisitely slow, almost undetectable at any given moment, but over millions and tens of millions of years, absolutely inexorable. The very fabric of the universe was being sculpted by this process. Matter was not distributing itself uniformly. It was gathering along certain paths and draining away from others. Denser regions grew denser. Emptier regions grew emptier. Over time, this produced a pattern that cosmologists call the cosmic web, an enormous, three-dimensional structure of filaments and nodes and sheets of matter, separated by vast, nearly empty voids. If you could see the entire observable universe from the outside, it would look something like a neural network or the structure of a sponge, with thin threads of matter connecting dense knots and enormous bubbles of emptiness in between. And the first structures to condense out of this cosmic web were not galaxies. They were not even gas clouds, at least not in the way we usually think of them. The first structures were dark matter halos. Dark matter, the invisible substance that makes up roughly 85% of all the matter in the universe. It is one of the most perplexing mysteries in modern science. We live in a cosmos mostly composed of something we cannot see, cannot touch, and do not understand. We know dark matter exists because its gravitational fingerprints are everywhere. Galaxies rotate faster than they should based on the mass of their visible stars and gas. The outer arms of spiral galaxies orbit at speeds that would fling them apart if ordinary matter were the only source of gravity holding them in place. Something unseen provides the extra pull. Galaxy clusters are bound together more tightly than their visible matter could account for. When Fritz Zwicky first noticed this discrepancy in the 1930s, he was largely ignored for decades. Vera Rubin, working in the 1970s, produced detailed rotation curves for dozens of spiral galaxies, all showing the same anomaly. Gravitational lensing observations, which measure how gravity bends light, consistently require more mass than can be seen, and the large-scale pattern of the cosmic web, the way galaxies are distributed across the sky in filaments and sheets and voids, matches computer simulations only when dark matter is included in enormous quantities. We do not know what dark matter is made of. It is not made of protons, neutrons, or electrons. It does not emit, absorb, or scatter light. It interacts with ordinary matter and with itself only through gravity and possibly through the weak nuclear force. It is, in the most literal sense of the word, invisible. We know it is there. We can measure its effects with precision, but we cannot see it, touch it, or detect it directly despite decades of effort. But dark matter's invisibility gives it a crucial advantage in the early universe. Because it does not interact with photons, dark matter was not held in place by the radiation pressure that prevented ordinary matter from clumping during the plasma era before recombination, while protons and electrons were bouncing photons back and forth and being pushed around by radiation pressure. Dark matter was free to start collapsing under gravity. It had a head start of hundreds of thousands of years by the time recombination occurred, and ordinary matter was finally released from the photon fog. Dark matter had already built an extensive invisible scaffolding of gravitational wells throughout the cosmos. These dark matter halos, as they are called, were concentrated nodes in the cosmic web. They came in a range of sizes, from relatively tiny ones with masses of perhaps 100,000 times the mass of our sun to larger ones with millions of solar masses, compared to a modern galaxy like the Milky Way, which contains a dark matter halo of roughly 1 trillion solar masses. These early halos were minuscule, but they were enough. The growth of these halos followed a pattern that cosmologists call hierarchical structure formation. Small halos formed first because small density fluctuations had less distance to collapse across and reached their critical density sooner. Over time, these small halos merged with each other, like raindrops combining on a windowpane, building up ever larger structures. Small halos merged to form medium halos. Medium halos merged to form large halos, eventually over billions of years. This bottom-up construction process produced the massive dark matter halos that host galaxies and galaxy clusters today. But in the first 100 million years, the halos relevant to the first stars were still quite small. The ones capable of forming stars, called mini-halos, typically had total masses of a few 100,000 to a few million solar masses. Only a fraction of that mass was ordinary matter. Most was dark matter, the ordinary matter, the hydrogen and helium gas that could actually collapse and form a star. constituted only about 15 to 16% of the total, matching the cosmic average ratio of ordinary matter to dark matter. These mini-halos were the locations where the first stars would form. But not all mini-halos were equal. Only those that exceeded a critical mass threshold, determined by the temperature of the infalling gas and the ability of molecular hydrogen to cool it, could actually produce stars. Halos that were too small did not have deep enough gravitational wells to heat the gas above the temperature where molecular hydrogen could begin to cool it. The gas would fall in, heat up, and then sit there in a stable warm equilibrium, unable to cool further and unable to collapse. These subthreshold halos remained sterile, dark clumps of gas and dark matter drifting through the cosmic web, waiting to merge with larger structures before their gas could participate in star formation. The halos that did cross the threshold, typically those with virial temperatures of about 1,000 Kelvin or higher, corresponding to total masses of roughly 1 million solar masses, were the cradles of the first generation. In these halos, the infalling gas was heated to temperatures where molecular hydrogen could begin to do its work. Their gravity reached out into the surrounding space and began to pull in ordinary matter, the hydrogen and helium gas that now filled the universe in its electrically neutral state. Gas streamed along the filaments of the cosmic web, funneling into the halos, accumulating at their centers. Over millions of years, dense clouds of hydrogen and helium gas built up inside these dark matter cocoons. These gas clouds were the nurseries of the first stars. But there was a problem, a serious problem, a fundamental problem that threatened to prevent stars from forming at all. And that problem was heat. Here is something that might seem counterintuitive, and it is worth spending some time on, because it is absolutely central to the story of the first stars. Gas that is falling into a gravitational well does not just quietly settle to the center and start forming a star. The process is much more violent and complicated than that. As gas falls toward the center of a dark matter halo, it accelerates. It is converting gravitational potential energy into kinetic energy, gaining speed as it plunges inward. And when this fast-moving gas reaches the center of the halo, or when infalling streams of gas collide with each other, all that kinetic energy has to go somewhere. It is converted into thermal energy, heat. The gas gets hot, very hot, in some cases reaching temperatures of thousands of degrees Kelvin. And hot gas has pressure. That pressure pushes outward, resisting further compression. It is the same basic principle that keeps our sun from collapsing under its own gravity right now. The sun is in a state of hydrostatic equilibrium. The inward pull of gravity is precisely balanced by the outward push of the hot gas pressure generated by nuclear fusion in its core. If you turned off fusion in the sun, the core would begin to contract under gravity, which would heat the gas, which would raise the pressure, which would partially resist the contraction. It is gravity versus pressure, and neither side wins easily. For a gas cloud to collapse far enough to form a star, it has to shed that thermal energy. It has to radiate energy away into space. It has to cool down. As it cools, it loses pressure support. Gravity gains the upper hand. The cloud compresses further, heats up again, must cool again, compresses further, in a cycle that continues until the core becomes dense, and hot enough for nuclear fusion to ignite. In the modern universe, this cooling process is relatively efficient. Gas clouds today are enriched with heavy elements, which astronomers call metals. And in astronomy, metal means everything heavier than helium. So carbon and oxygen are metals in astronomer speak. These heavy elements are superb at radiating energy. When an atom of carbon or oxygen is hit by another particle, the collision excites the atom's electrons to higher energy levels. Almost immediately, the electron drops back down and releases a photon, which carries energy away from the cloud. Carbon, oxygen, silicon, iron, and other metals act as extraordinarily effective cooling agents, allowing modern gas clouds to shed heat rapidly, collapse efficiently, and fragment into many smaller clumps. Each clump forms a relatively modest star, a star like our sun, or a red dwarf even smaller, or a massive blue giant. The modern universe produces a wide range of stellar masses because enriched gas can cool to very low temperatures and fragment freely. But the first gas clouds had no heavy elements, none at all. Their composition was exactly what the Big Bang had provided, nothing more, nothing less. Hydrogen, helium, and a vanishingly small trace of lithium. And pure hydrogen and helium gas are remarkably bad at cooling. Neutral hydrogen atoms can radiate energy, but only at specific, relatively high temperatures. The primary mechanism is called Lyman alpha emission, where a hydrogen atom excited to a higher energy state drops back to its ground state and emits an ultraviolet photon. This process only works efficiently above about 10,000 degrees Kelvin. Below that temperature, neutral hydrogen atoms are very poor radiators. They sit there, holding onto their thermal energy like a stubborn child clutching a toy. Helium is even worse. Its energy levels are spaced farther apart, meaning it requires even higher temperatures to be excited and emit radiation. In the temperature range relevant to star formation, a few hundred to a few thousand degrees, helium is essentially useless as a coolant. This posed an enormous challenge for the early universe. Without efficient cooling, the primordial gas clouds could not collapse. Without collapse, there could be no stars. And without stars, the universe would remain in darkness forever. It seemed as though the dark ages might be permanent. But nature found a way. And the solution came from a molecule so simple, so fragile, and so cosmically rare that it almost seems absurd that it held the key to everything that followed. That molecule was molecular hydrogen. H2, two hydrogen atoms bonded together. Molecular hydrogen is one of the simplest molecules in existence. Two protons share two electrons in a covalent bond. In the modern universe, it is everywhere, the primary component of the giant molecular clouds that spawn new stars in galaxies like our own. But in the modern universe, molecular hydrogen forms easily on the surfaces of dust grains, those tiny solid particles of silicon, carbon, and ice that pervade interstellar gas. An atom of hydrogen lands on a dust grain, sticks there, waits for another hydrogen atom to land nearby, and the two combine on the surface, with the grain absorbing the excess energy. It is an efficient process, almost casual in its simplicity. But in the primordial universe, there were no dust grains. Dust is made of heavy elements, silicon dioxide, iron oxides, carbonaceous material, things that did not exist yet because no star had ever created them. Without dust grains, molecular hydrogen had to form through a much more roundabout and inefficient chemical pathway, a gas phase reaction that relied on an unlikely intermediary. Here is how it worked. Despite recombination, a very small number of free electrons still existed in the primordial gas, roughly 1 in every 10,000 hydrogen atoms. These leftover electrons had avoided capture during recombination, a statistical inevitability in any finite temperature process. Occasionally, one of these free electrons would encounter a neutral hydrogen atom and attach itself, forming a negatively charged hydrogen ion, denoted H-. This H- ion is extraordinarily fragile. Its extra electron is only weakly bound, barely held in place by the attraction to the single proton at the atom's center. Any moderately energetic photon could knock it loose. Most H- ions were destroyed almost as soon as they formed, either by photons from the cosmic microwave background or by collisions with other particles. But occasionally, very occasionally, an H- ion survived long enough to encounter another neutral hydrogen atom. In that collision, the extra electron could be transferred, forming a covalent bond between the two hydrogen nuclei. A molecule of H2 was created, and the original electron was released back into the gas, free to participate in the process again. It was a catalytic reaction, with the free electron serving as a catalyst that was not consumed in the process. The rate of this reaction was painfully slow. Only a tiny fraction of the available hydrogen was converted to molecular form. In a typical primordial gas cloud, the molecular hydrogen fraction reached perhaps a few parts in 1,000, sometimes even less. By comparison, the molecular fraction in a modern star-forming cloud might be 90% or higher. The primordial clouds were operating with an almost negligible amount of their key coolant. And yet, it was enough. Barely enough, teetering on the knife's edge of being enough. But enough. Molecular hydrogen can cool gas through a mechanism that is fundamentally different from how atoms cool. When two H2 molecules collide, the kinetic energy of the collision can excite one of the molecules into a higher rotational or vibrational state. The molecule spins faster, or its two atoms vibrate more energetically against their bond. This excited state is unstable. Within a short time, the molecule drops back to a lower state and emits a photon, carrying away a small packet of energy. That photon flies out of the cloud, taking energy with it. The cloud cools, one tiny photon at a time. The energy gaps between rotational levels in H2 correspond to temperatures of a few hundred Kelvin, which means H2 can cool gas at temperatures far below those where atomic hydrogen becomes effective. This was the crucial advantage. Atomic hydrogen goes silent below 10,000 Kelvin. Molecular hydrogen keeps radiating down to about 200 Kelvin, in the temperature range relevant to the first gravitational collapses. Molecular hydrogen was the only coolant available. It was the only path from hot gas to cold gas, from pressure support to gravitational collapse, from darkness to starlight, as molecular hydrogen slowly accumulated in the cores of primordial gas clouds. Sitting inside dark matter halos, that had been growing for tens of millions of years. It began to do its quiet, essential work. Photon by photon, collision by collision, it radiated heat away from the cloud. The temperature dropped. From several thousand degrees, it fell to about 1,000, then to 500, then gradually down toward 200 Kelvin. It was an agonizingly slow process. Molecular hydrogen is a much weaker coolant than metals like carbon and oxygen. Where a modern enriched gas cloud might cool to its final temperature in a few tens of thousands of years, a primordial cloud relying on molecular hydrogen cooling might take millions of years to reach equilibrium. But time was the one resource the universe had in abundance, and as the gas cooled, it lost pressure support. Gravity, patient gravity, gained the upper hand. The cloud began to contract. As it contracted, the density increased, which allowed more molecular hydrogen to form, which improved the cooling slightly, which allowed further contraction. A virtuous cycle, gravity feeding on itself, drawing the gas inward in an ever-tightening spiral. But because molecular hydrogen is such an inefficient coolant compared to metals, the gas could not cool as much as modern star-forming clouds do. Modern clouds cool to 10 or 20 Kelvin. Primordial clouds could only reach about 200 Kelvin. And this difference in temperature had a profound, far-reaching consequence for the stars that formed. The concept at play here is called the Jeans mass, named after the British physicist Sir James Jeans, who first described it in the early 1900s. The Jeans mass is the minimum mass a gas cloud must have in order for its gravitational pull to overcome the outward push of thermal pressure and cause collapse. It depends on two things: the temperature and the density of the gas. Higher temperature means higher pressure, means larger Jeans mass. You need a bigger cloud to collapse. Lower temperature means lower pressure, which means a smaller Jeans mass. And even relatively small clouds can collapse. Because the first gas clouds were stuck at about 200 Kelvin, their Jeans mass was enormous compared to modern star-forming conditions. Hundreds, even thousands of solar masses, instead of fragmenting into many small clumps that would each form a sun-like star, as happens in the metal-enriched clouds of the modern Milky Way. These primordial clouds tended to collapse into one or a few very large, very massive clumps. To appreciate how different this was from modern star formation, consider what happens in the Milky Way today. In a region like the Orion Nebula, about 1,300 light-years away, giant molecular clouds with temperatures of 10 to 20 Kelvin collapse and fragment into thousands of individual clumps. The resulting stars span a wide range of masses, from tiny red dwarfs with a tenth of the sun's mass to occasional blue giants tens of times heavier. But the most common outcome is a star roughly half the mass of the sun or smaller. The vast majority of stars born in the modern universe are dim, small, long-lived red dwarfs. This is because efficient metal line cooling allows the gas to reach very low temperatures, which drives the Jeans mass down to small values, which favors the formation of small stars. In the primordial universe, the situation was entirely reversed. The floor temperature of 200 Kelvin, set by the limitations of molecular hydrogen cooling, kept the Jeans mass stubbornly high, and there was an additional factor that pushed the masses even higher. As the gas cloud collapsed, it heated up again through compressional heating, and at a certain point, the molecular hydrogen began to dissociate, breaking apart into individual atoms. This happened at temperatures of roughly 2000 Kelvin. The dissociation absorbed enormous amounts of energy, temporarily halting the collapse, but it also removed the very coolant that had enabled the collapse in the first place. The gas entered a brief period of chaotic readjustment before eventually collapsing further. Now relying on atomic hydrogen line cooling at higher temperatures, the protostellar core that formed at the center of this collapse was typically much hotter and much more massive than a modern protostar. Computer simulations show that accretion onto this core continued at a ferocious rate, roughly 1,000th to 100th of a solar mass per year, compared to a typical accretion rate onto a modern protostar of 1/1,000,000th of a solar mass per year. The primordial protostar was gaining mass 1,000 times faster than our sun did during its birth. Surrounding the growing protostar was an accretion disk, a swirling disk of infalling gas feeding the central object, similar in structure to accretion disks around modern protostars, but larger and more massive in every respect. This accretion continued until something shut it off. In the most massive cases, the growing star eventually became so hot and luminous that its radiation ionized the surrounding gas and drove it away, cutting off its own fuel supply. This radiative feedback set an effective upper limit on the mass that a first-generation star could reach, though the exact value of that limit remains debated and likely depends on the specific geometry and angular momentum of the collapsing cloud. The result was a generation of stars unlike anything the universe has produced since. Stars of staggering mass, blinding luminosity, and heartbreakingly short lives. The first stars, they are called population 3 stars, and the name itself is one of those charming accidents of scientific history, where the numbering goes precisely backward from what you might logically expect. The story begins in the 1940s at the Mount Wilson Observatory above Pasadena, California, where the German-born American astronomer Walter Baade was taking advantage of wartime blackout conditions, with the lights of Los Angeles dimmed to protect against potential Japanese air raids. The skies above Mount Wilson were unusually dark. Baade used the 100-inch Hooker telescope, then the most powerful in the world, to study the stars of the Andromeda galaxy with unprecedented clarity. He noticed something interesting. Stars in Andromeda seemed to fall into 2 distinct groups with noticeably different characteristics. Younger, hotter, bluer stars rich in heavy elements were concentrated in the galaxy's spiral arms and disk. He called these population 1. Older, cooler, redder stars with much lower abundances of heavy elements dominated the central bulge, and the globular clusters that orbited the galaxy like a swarm of ancient satellites. He called these population 2. The numbering reflected the order of discovery and ease of observation, not the order in which these stars had actually formed. Decades later, in the late 1970s, when theorists began to work out what the very first stars in the universe must have been like, stars that predated even the ancient population 2 stars, they realized they needed a new category. Following the existing convention, these hypothetical first-generation stars were designated population 3. the first stars to exist, but the last to be named, and still the hardest to find. Our own sun is a comfortable population 1 star, born roughly 4.6 billion years ago from gas that had been enriched by perhaps 7 or 8 billion years of previous stellar activity. It contains about 2% heavy elements by mass, enough for rocky planets, complex chemistry, and ultimately life. It is a middle-aged, middle-mass, middle-of-the-road star in nearly every respect. Population: 3 stars were none of these things. 3 stars formed from gas that was completely pristine, untouched by any previous generation of stellar processing. No carbon, no oxygen, no iron, no silicon, just hydrogen, helium, and the faintest trace of lithium. This chemical purity, combined with the high Jeans mass we discussed, gave them properties that are profoundly, dramatically different from any star shining in the universe today. Computer simulations of first star formation have become remarkably sophisticated over the past 2 decades, incorporating detailed models of dark matter halo growth, primordial gas chemistry, molecular hydrogen cooling, and gravitational collapse in 3 dimensions. The results consistently indicate that the first stars were massive, much more massive than a typical star today. While the exact mass distribution remains debated, and some models allow for the formation of more modest first stars in the range of 10 to 30 solar masses, many simulations produce stars of 50, 100, or even several hundred times the mass of our sun. Recent simulations, including groundbreaking work by Ki-Young Chen and colleagues at the Institute of Astronomy and Astrophysics at Academia Sinica in Taiwan, published in 2025, have revealed an additional layer of complexity. These simulations show that violent turbulence in the collapsing primordial gas clouds played a significant role in determining how many stars formed and how massive they were. Instead of a single monolithic collapse into one giant star, the turbulent gas sometimes fragmented into several clumps of different sizes, raising the possibility that the first stellar populations were more diverse than earlier, simpler models had suggested. Some of these clumps might have been relatively modest, only about 8 solar masses, while others could have been much larger. Still, the consensus remains that population 3 stars were, on average, substantially more massive than modern stars, and mass determines everything about a star's character. A star of 100 solar masses is not just 100 times more impressive than the sun. It is qualitatively different. Its luminosity, the total amount of energy it radiates per second, scales roughly with the 3rd or 4th power of its mass. A star 100 times the mass of the sun does not shine 100 times brighter. It shines roughly 1,000,000 times brighter, or even more. Its surface temperature would be scorching, around 80,000 to 100,000 Kelvin, compared to the sun's 5,800. At that temperature, the star does not glow the warm yellow-white of our sun. It blazes a fierce, brilliant blue-white, almost colorless to human eyes in its intensity, emitting the vast majority of its energy in the far ultraviolet. Radiation so energetic it can tear electrons from atoms, shatter molecules, and ionize gas across thousands of light years. Now imagine the scene. For 100 million years or more, the universe has been utterly dark. Not a single photon of visible light exists anywhere. Dark matter halos have been silently growing, pulling gas into their centers. In one particular halo, a cloud of hydrogen and helium has been cooling for millions of years via the tortuously slow process of molecular hydrogen radiation. The cloud has contracted and contracted and contracted. Its core has grown denser and hotter, a ball of gas roughly the size of our entire solar system, pressed inward by gravity, heated by compression. And then, the core temperature reaches approximately 10 million Kelvin. At that temperature, hydrogen nuclei, protons, are moving fast enough that, when they collide, they can overcome the electrostatic repulsion between their positive charges and fuse. The strong nuclear force grabs them, locks them together. Deuterium forms, then helium-3, then helium-4. Each reaction releases a burst of energy. A chain reaction begins, self-sustaining, feeding on itself. The core ignites. Energy floods outward from the center. Radiation pressure builds, pushing against the infalling gas. The collapsing cloud halts, stabilizes, and finds a new equilibrium. A star is born, and with it, light returns to the universe, a sphere of blue-white fire, hundreds of times the diameter of our sun, blazing with the fury of 1,000,000 suns or more, erupts into existence in the heart of the darkness. Ultraviolet radiation streams outward at the speed of light, slamming into the surrounding neutral hydrogen gas, ripping electrons from atoms, creating an expanding bubble of hot, ionized, glowing gas. Within this bubble, the universe is lit. Outside it, the darkness persists. For the first time since the cosmic microwave background was released 380,000 years after the Big Bang, there is a new source of light in the cosmos, not ancient, stretched, cooled radiation from the primordial fireball, but fresh photons, born in nuclear fires, carrying the energy of creation. The eternal night had lasted for over 100 million years, and now, in a single cosmic instant, it had been punctured by a point of light. But this star was not alone for long. Across the observable universe, in other dark matter halos, other gas clouds were going through the same process. Within a few million years, dozens, then hundreds, then thousands of first stars began to ignite, scattered across the cosmos like the first sparks of a fire that would eventually set the entire universe ablaze. This gradual illumination, this slow transition from the utter blackness of the dark ages to the first scattered glows of starlight, is what astronomers call the cosmic dawn. It was not a moment, it was an era, stretching from perhaps 100 million years to roughly 1 billion years after the Big Bang. And during this era, the first stars did not just sit there shining passively into the void. They actively, violently, irrevocably transformed the universe around them. Even while they were still alive, population 3 stars began reshaping their cosmic neighborhoods in dramatic ways. Their ultraviolet radiation did not only ionize hydrogen, it also destroyed molecular hydrogen in neighboring gas clouds, the very coolant that other clouds needed to collapse and form stars of their own. A single luminous population 3 star could sterilize the gas in surrounding mini-halos for thousands of light years, preventing or delaying star formation in those regions. This is called radiative feedback, and it created a strange, self-limiting effect. The first stars, by their very existence, temporarily suppressed the birth of additional first stars in their vicinity. This negative feedback slowed the early stages of star formation, spreading the process out over millions of years, rather than allowing a single burst of star formation across the entire universe. Some theoretical models suggest that this feedback was strong enough to create a patchy, intermittent pattern of early star formation, with individual population, 3 stars turning on and off across the cosmic landscape, like scattered fireflies, rather than a steady flood of light. But the destruction of molecular hydrogen was only temporary. When a population 3 star died, its radiation ceased, and the surrounding gas could slowly begin to rebuild its molecular hydrogen content and resume cooling. And when that star died in a supernova, the shock wave from the explosion compressed nearby gas clouds, actually triggering new rounds of star formation. This is called positive feedback, and it worked in the opposite direction from radiative feedback, promoting the birth of new stars rather than suppressing it. The interplay between these two competing feedback mechanisms, the negative feedback of radiation destroying coolant molecules, and the positive feedback of supernovae compressing and enriching gas, was enormously complex. Understanding this interplay and how it shaped the rate and pattern of early star formation remains one of the central challenges in the theoretical study of the cosmic dawn. Computer simulations must track the birth, radiation, and death of individual population 3 stars, the chemistry of molecular hydrogen formation and destruction, the propagation of supernova shock waves, the mixing of heavy elements into the primordial gas, and the collapse of new gas clouds into second-generation stars, all simultaneously across cosmological volumes. It is one of the most computationally demanding problems in all of astrophysics. To understand the full impact of these first stars, we need to talk about how they lived, and more importantly, how they died. Because the death of a population 3 star was not a quiet fading. It was one of the most violent events the universe has ever produced. The most massive stars in the universe are, paradoxically, the shortest lived. This seems backward, almost unfair. You might expect that a star with 100 times the mass of the Sun would have 100 times as much fuel, and therefore burn for 100 times as long. But stars are not like candles. The rate at which a star burns its fuel is not proportional to the amount of fuel it has. It is proportional to a much higher power of its mass, roughly the cube. A star twice as massive as the Sun burns fuel not twice as fast, but roughly 8 times as fast. A star 100 times the mass of the Sun burns fuel at a rate so ferocious that it exhausts its supply in a tiny fraction of the time the Sun will take. Our Sun, a modest population 1 star, will shine for roughly 10 billion years on the main sequence, steadily fusing hydrogen into helium in its core. It is currently about halfway through its life. A population 3 star of 100 solar masses would burn through its hydrogen in perhaps 2 to 3 million years. The very most massive stars of several hundred solar masses might have lived for as little as 2 million years. 2 million years. Homo erectus, one of our distant ancestors, first appeared on Earth roughly 2 million years ago. The entire time span that separates us from the earliest upright walking members of our lineage, would barely encompass the entire life of the most massive first star. In cosmic terms, these stars were born and died in a flash. But during their brief lives, they burned with an intensity that is difficult to overstate. In their cores, hydrogen fused into helium at a staggering rate. The energy released by this fusion maintained the tremendous radiation pressure needed to support a star of such enormous mass against gravitational collapse. The core temperature hovered at tens of millions of degrees. The entire star was a churning, convecting ball of plasma, energy fighting gravity in a battle that gravity would eventually win. As the hydrogen in the core was depleted, replaced by an inert ball of helium ash, the core contracted without hydrogen fusion to support it. Gravity compressed the helium core, raising its temperature and density until helium itself began to fuse. At roughly 100 million degrees Kelvin, helium nuclei combine through the triple alpha process. 3 helium-4 nuclei colliding and sticking together to form carbon-12. Some of that carbon captured another helium nucleus to become oxygen-16. The star had entered the next phase of its life, burning helium in its core, while hydrogen continued to fuse in a shell surrounding the core. Helium burning was faster than hydrogen burning. It lasted perhaps a few 100,000 years. When the helium was exhausted, the core contracted again, the temperature rose again, and carbon fusion ignited. Carbon nuclei fused to produce neon, sodium, and magnesium. This phase lasted only a few hundred to a few thousand years. Then, neon burning began, lasting perhaps a year. Then, oxygen burning, lasting months. Then, silicon burning, the final stage, lasts perhaps a single day. Each successive burning stage was shorter than the last, an accelerating cascade of nuclear transformation. The star developed an onion-like structure with concentric shells of different composition. A thin outer layer of hydrogen still fusing at the periphery, a layer of helium fusion beneath, then carbon, then neon, then oxygen, then silicon, each shell hotter and denser than the one above. And at the very center, growing larger by the hour, an inert core of iron and nickel. Iron is the end of the road for exothermic nuclear fusion. Fusing iron does not release energy. It absorbs it. The iron core grows, supported by a combination of electron degeneracy pressure and thermal pressure. But it cannot generate energy to support itself. It is a dead weight at the heart of the star, growing heavier with each passing moment as silicon fusion rains iron ash down upon it. And when the core reaches approximately 1.4 solar masses, electron degeneracy pressure can no longer support it. The core collapses. For stars in a certain mass range, the collapse triggers a core collapse supernova. The infalling material bounces off the impossibly dense core, generating a shock wave that tears the star apart from the inside out. The outer layers are blasted into space at thousands of kilometers per second, enriched with all the elements the star forged during its lifetime. A neutron star or black hole is left behind. But for population, 3 stars in the mass range of roughly 140 to 260 solar masses. A different and even more spectacular fate awaited: the parent stability supernova. In the cores of these extremely massive stars, temperatures eventually exceed roughly 300 million degrees Kelvin. At these temperatures, the photons filling the star's interior carry so much energy that when two of them collide, they can spontaneously convert into a pair of particles, an electron and a positron, its antimatter counterpart. This process is called pair production, and it has a devastating consequence. Those photons were providing radiation pressure, the outward force that was keeping the star's core from collapsing. By converting photon energy into mass, pair production effectively drains the radiation pressure. The support structure of the star weakens. The core begins to implode, but this implosion, unlike the iron core collapse that triggers ordinary supernovae, compresses and heats the remaining nuclear fuel, primarily oxygen and silicon, to such extreme temperatures that it detonates, not a slow, controlled burn, a thermonuclear explosion. The star does not just collapse and bounce. It is blown apart by a runaway nuclear detonation that is so powerful, so energetic, that it completely destroys the star. Nothing is left behind. No neutron star, no black hole, no remnants at all. The entire star, 150 or 200 solar masses of hydrogen, helium, carbon, oxygen, silicon, iron, and everything in between, is vaporized and scattered into intergalactic space at a significant fraction of the speed of light. The explosion can, for a brief time, outshine an entire galaxy. It is among the most violent events known to physics. And critically, apparent stability supernova scatters enormous quantities of heavy elements into the surrounding gas. A single such explosion can eject dozens of solar masses worth of metals into intergalactic space. Carbon, oxygen, silicon, magnesium, sulfur, iron, nickel, and many other elements that did not exist anywhere in the universe before this star created them are now free. They mix with the surrounding pristine hydrogen and helium. They change the chemistry of the cosmos permanently and irreversibly. For stars even more massive than about 260 solar masses, the story ends differently and more darkly. In these monsters, a process called photodisintegration occurs after the initial pair instability collapse. The gamma rays produced during the collapse are so energetic that they smash apart heavy nuclei, undoing the very fusion that was supposed to power the explosion. This absorbs the energy that would have blown the star apart. Instead of a supernova, the star collapses entirely into a black hole, swallowing its heavy elements and leaving behind only a gravitational scar in the fabric of spacetime. Some of these first-generation black holes may have become the seeds of the supermassive black holes that we now observe at the centers of galaxies. Monsters weighing millions or billions of solar masses that power quasars and active galactic nuclei. Together, the various deaths of the first stars, pair instability supernovae, core collapse supernovae, and direct collapses to black holes, initiated the process of cosmic chemical enrichment. Before the first stars, the universe contained only hydrogen, helium, and lithium. After the first generation lived and died, the gas of the cosmos was seeded with traces of carbon, oxygen, silicon, iron, and many other elements. This was the first step in a process called cosmic chemical evolution, the gradual enrichment of the universe's gas over billions of years of stellar birth, life, and death. And it changed everything that came after. The enrichment was not uniform. The metals ejected by a supernova did not spread evenly throughout the universe. Instead, they formed expanding bubbles and shells of enriched gas around the explosion sites, mixing turbulently with the surrounding pristine hydrogen over thousands to millions of years. Some regions of the cosmos received large doses of metals from nearby supernovae. Others, particularly those in the voids far from any dark matter halo where stars had formed, remained pristine for much longer. Theoretical calculations have shown that there is a critical metallicity threshold, a minimum abundance of heavy elements in a gas cloud, above which the cloud's cooling behavior changes fundamentally. That threshold is extraordinarily low, roughly 100,000th of the sun's metal abundance. Once a gas cloud exceeds this threshold, carbon and oxygen line cooling becomes effective enough to cool the gas to temperatures far below what molecular hydrogen alone could achieve. The gene's mass drops precipitously. The cloud fragments into many smaller pieces. The era of massive, solitary population, 3 stars, gives way to a new mode of star formation that produces many smaller, more diverse stars. This transition from population 3 to population 2 star formation did not happen all at once across the universe. It happened locally, in individual dark matter halos, as the metals from each supernova mixed with the surrounding gas. In some halos, the transition happened early, after just 1 or 2 supernovae had enriched the gas past the critical threshold. In others, particularly in regions that were more isolated or received smaller doses of metals, population 3-style star formation may have continued for much longer. Theoretical models suggest that traces of metal-free star formation may have persisted in the most remote and pristine corners of the cosmos for hundreds of millions of years after the first stars appeared, gradually fading as the expanding web of chemical enrichment reached even the most isolated halos. But the overall trend was clear and irreversible. The universe was becoming chemically complex. With each generation of stars that lived and died, the gas was enriched further, pushing it past the critical metallicity threshold in more and more locations. The giant blue-white monsters of the cosmic dawn were giving way to a more familiar stellar landscape, one populated by stars spanning a wide range of masses, including the small, long-lived stars that could survive to the present day. The first stars did not merely scatter heavy elements into space when they died in their spectacular supernovae. While they were alive, burning with that extraordinary blue-white fury, they were engaged in an equally dramatic transformation of the universe around them. They were tearing apart the fog. After recombination, the universe was filled with neutral hydrogen gas. This gas was transparent to most wavelengths of visible and infrared light, which is why we can observe the cosmic microwave background today. But it was extremely effective at absorbing one particular kind of radiation: ultraviolet photons with energies above 13.6 electron volts, the energy required to knock the single electron off a hydrogen atom and ionize it. Any ultraviolet light at those energies or above would be absorbed by neutral hydrogen before it could travel very far. The universe had traded the plasma fog of its first 380,000 years for a new kind of opacity, a fog of neutral hydrogen that blocked ultraviolet radiation. And population 3 stars, with their scorching surface temperatures of 80,000 to 100,000 Kelvin, produced enormous quantities of ultraviolet radiation. They emitted far more energy in the ultraviolet than in visible light. These photons streamed outward from the star and slammed into the surrounding neutral hydrogen. Each photon with sufficient energy ionized one hydrogen atom, knocking its electron free. The result was a bubble of ionized hydrogen, a region where the gas had been stripped of its electrons and was now a hot plasma, transparent to ultraviolet light. Around each population 3 star, this ionized bubble grew outward like an expanding sphere of clarity in the cosmic fog. Inside the bubble, light traveled freely. Outside the bubble, neutral hydrogen still absorbed ultraviolet photons. The first stars were carving private windows of transparency into the opaque universe. Initially, these bubbles were small. A single star, no matter how luminous, could only ionize so much gas before its radiation was overwhelmed by the sheer density of surrounding neutral hydrogen. But as more stars ignited across the universe, and especially as the first primitive galaxies began to form, clustering many stars together in a small region, the bubbles grew. They expanded, met each other, and merged. Neighboring bubbles overlapped, combining into larger and larger regions of ionized gas. This process is called cosmic reionization, and it represents one of the most dramatic phase transitions in cosmic history. The universe's hydrogen had been ionized once before, in the hot plasma before recombination. Recombination neutralized it. Now, the first stars and galaxies were ionizing it all over again, from the outside in, bubble by bubble. Reionization was not instantaneous, and it was not uniform. It was a long, patchy, complicated process that took hundreds of millions of years to complete. Some regions of the universe, those near concentrations of star-forming dark matter halos, were reionized early. Others, particularly regions where the cosmic web was thinner and fewer galaxies had formed, remained neutral for much longer. If you could watch a time-lapse of reionization from some impossible vantage point outside the universe, you would see a mesmerizing spectacle. Against a background of dark, neutral hydrogen fog, tiny pinpricks of light would appear, each one a galaxy or proto-galaxy, surrounded by its growing bubble of ionized gas. The bubbles would expand, at first slowly, then faster as the galaxies within them grew brighter and more numerous. Neighboring bubbles would touch, merge, and combine into larger ionized regions. The neutral hydrogen between them would shrink into ever smaller islands and filaments, like patches of ice melting in a warming sea. Some stubborn pockets of neutral gas, particularly in the densest regions of the cosmic web, where recombination was fastest, would hold out longer than their surroundings. But eventually, relentlessly, the tide of ionization would sweep over them too. The pattern would not be random. It would follow the structure of the cosmic web, with the first and largest ionized regions forming along the densest filaments and nodes where galaxies were concentrated, and the last holdouts of neutral gas persisting in the less dense regions between. The entire process would look like a vast, cosmic-scale sunrise, with dawn breaking first in the busiest neighborhoods of the universe and spreading outward, until even the most remote corners of the cosmos were flooded with ultraviolet light. Computer simulations of reionization, which model the formation and growth of billions of ionized bubbles across cosmological volumes, produce predictions that can be tested against observations. And in recent years, those observations have begun to deliver. The timeline of reionization has been narrowed considerably by observations. Early clues came from the cosmic microwave background itself. The free electrons produced during reionization scattered some of the CMB photons, imprinting a subtle signature in the CMB's polarization pattern. Measurements by the Planck satellite suggested that reionization began somewhere around 200 to 300 million years after the Big Bang. More precise constraints have come from the spectra of distant quasars. Quasars are extraordinarily luminous active galactic nuclei powered by supermassive black holes, and some of them are so distant that their light has been traveling since the epoch of reionization. As this light passes through intergalactic hydrogen on its way to us, neutral hydrogen absorbs specific wavelengths. By examining these absorption patterns, astronomers can determine how much neutral hydrogen existed along the line of sight at various distances, and therefore at various cosmic times. The key spectral feature is called the Lyman alpha line, an ultraviolet emission line produced by the most common electronic transition in hydrogen. When a quasar's light travels through intergalactic gas, any neutral hydrogen along the path absorbs the Lyman alpha photons, creating a characteristic absorption signature. For quasars observed at moderate distances, this absorption appears as a dense forest of narrow lines in the spectrum, each one caused by a separate cloud of hydrogen at a different distance along the line of sight. This is called the Lyman alpha forest, and it provides a kind of barcode of the universe's large-scale structure, revealing the distribution of gas between galaxies. But for quasars at very great distances, corresponding to times when reionization was still underway, the absorption becomes so strong and so continuous that the quasar's light is completely absorbed on the blue side of the Lyman alpha line. This total absorption, called the Gunn-Peterson trough, after the physicists who predicted it in the 1960s, indicates that a significant fraction of the intergalactic hydrogen was still in its neutral state. The presence or absence of this trough at different redshifts tells astronomers when and where reionization was complete. Furthermore, studies of a feature called damping wing absorption in the spectra of the most distant known quasars have provided even more detailed information about the state of the intergalactic medium during reionization. A quasar designated ULAS Joan 1000 342 plus 928, observed at a cosmological redshift of 7.54, corresponding to roughly 700 million years after the Big Bang, shows clear evidence of a substantially neutral intergalactic medium around it. This tells us that even 700 million years after the birth of the cosmos, the Great Clearing was still in progress. The universe was still shaking off the last remnants of its neutral fog. A landmark study led by Sarah Bosman at the Max Planck Institute for Astronomy used quasar spectra to precisely time the end of reionization at approximately 1.1 billion years after the Big Bang. This settled a debate that had lasted for decades and pushed the end of reionization significantly later than many earlier estimates had suggested. The conclusion that reionization ended this late was itself surprising, because it implied that the process was highly drawn out and patchy, with some regions of the universe remaining significantly neutral long after others had been fully ionized. The sources of reionization were diverse. The massive population 3 stars certainly contributed, especially in the earliest stages. But by the time reionization was in full swing, the first generation of giants had mostly died. The heavy elements they scattered had enriched the surrounding gas, enabling a new generation of stars, population 2, to form. These second-generation stars were generally smaller and less massive than their predecessors, thanks to the improved cooling provided by metals in the gas. But they formed in much greater numbers. The transition from isolated population 3 stars to collections of stars organized into primitive galaxies was driven partly by the continued growth and merging of dark matter halos. As time went on, the mini-halos that had hosted the first stars merged with each other through gravitational interaction, building up larger and larger structures. Eventually, some of these merged halos exceeded a critical mass threshold of roughly 100 million solar masses, at which point they became what cosmologists call atomic cooling halos. In these larger halos, the infalling gas was heated to temperatures above roughly 10,000 Kelvin, hot enough for atomic hydrogen itself, not molecular hydrogen, to become an effective coolant. Atomic hydrogen cools through the emission of Lyman alpha photons when its electron drops from the second energy level to the ground state, a process that is far more efficient than molecular hydrogen cooling. This new cooling channel meant that gas in atomic cooling halos could cool and collapse much more readily than in the smaller mini-halos. Star formation became more vigorous, more sustained, and less dependent on the fragile molecular hydrogen that had enabled the first stars. Gas accumulated at the centers of these halos, forming dense concentrations of young stars, the first primitive galaxies. These were not the grand spiral and elliptical galaxies we see today. They were small, irregular, clumpy collections of a few thousand to perhaps a few million stars, embedded in their dark matter halos, like bright seeds in dark soil. But they were the ancestors of every galaxy in the modern universe, including our own Milky Way. Early galaxies, tiny by modern standards, but containing thousands to millions of these second-generation stars, became the primary engines driving reionization forward. Recent observations with the James Webb Space Telescope have provided compelling evidence that small, faint dwarf galaxies, far too dim to have been observed by earlier telescopes, may have been the dominant drivers of reionization. Collectively, these swarms of small galaxies poured out enough ultraviolet radiation to gradually clear the neutral hydrogen fog across the entire observable universe. The photon budget for reionization, the total number of ionizing photons required to strip the electrons from all the neutral hydrogen in the intergalactic medium, is staggering. By some estimates, it required roughly 10 ionizing photons for every hydrogen atom in the universe, because ionized hydrogen recombines and must be reionized multiple times before the density drops low enough for the ionized state to persist. By about 1 billion years after the Big Bang, the job was essentially done. The intergalactic medium was almost entirely ionized. Light could travel freely through space in all directions, at all wavelengths. The cosmic dark ages were definitively over. The cosmic dawn had given way to a transparent, illuminated universe, a universe that looked, in its broad outlines, recognizably similar to the one we observe today. The great fog had been burned away. The universe was clear, and within that cleared cosmos, the grand era of galaxy formation and evolution could proceed, building the structures that would eventually produce the universe we observe around us today. Spiral galaxies and elliptical galaxies, galaxy clusters and superclusters, quasars and active nuclei, and the long, luminous filaments of the cosmic web stretching across billions of light years. The deaths of the first stars set in motion a chemical cascade that would ripple through billions of years of cosmic history. The elements they created and scattered became the raw material for subsequent generations of stars, each one more chemically enriched than the last. Second-generation stars, formed from gas enriched by population 3 supernovae, contained small but crucial amounts of carbon, oxygen, and other metals. When these stars died, they scattered even more heavy elements. Third-generation stars were richer still. And so it went, generation after generation, the chemical complexity of the universe increasing with each cycle. This process of chemical enrichment changed the very nature of star formation in ways that are difficult to overstate. With metals available as coolants, gas clouds could cool to much lower temperatures, allowing them to fragment into many smaller clumps. The average mass of newly formed stars decreased over cosmic time, where the first generation had been dominated by behemoths of 50 to several hundred solar masses. Later generations included a much wider range, from massive blue giants to modest sun-like stars to tiny red dwarfs weighing only a tenth of the sun's mass. The emergence of low-mass stars was particularly significant because low-mass stars are extraordinarily long-lived. A red dwarf with half the mass of the sun might burn its hydrogen fuel for 80 billion years, roughly 6 times the current age of the universe. A star with a quarter of the sun's mass could last for trillions of years. These tiny, dim, patient stars, invisible to the naked eye even from the nearest stellar neighborhoods, are by far the most common type of star in the modern universe. Roughly 75% of all stars in the Milky Way are red dwarfs. They outnumber all other stellar types combined, many times over. And many of the small, metal-poor stars born in the first billion years after the Big Bang are still shining today. They are stellar Methuselahs, ancient beyond reckoning, burning their fuel so slowly that they have barely aged in the 13 billion years since their birth. They drift through the halo of the Milky Way, orbiting the galactic center on long, eccentric paths that take them far from the disk, where younger stars like our sun reside. Some lurk in the ancient globular clusters, spherical swarms of hundreds of thousands of stars that orbit the Milky Way like miniature satellite galaxies. Others have been found hiding in the disk itself, apparently deposited there by ancient mergers between the Milky Way and smaller galaxies that it consumed billions of years ago. These ancient survivors carry in their atmospheres the chemical fingerprints of the first supernovae that enriched them. They are cosmic time capsules, preserving a record of conditions in the early universe that is otherwise inaccessible to observation. And this realization gave birth to the field of stellar archaeology, one of the most ingenious and productive subdisciplines of modern astronomy. The logic is elegant, since we cannot observe population 3 stars directly, because they all died billions of years ago. We can study their legacy by examining the most ancient surviving stars in our own Milky Way galaxy. These extremely metal-poor stars, found primarily in the galactic halo and in ancient dwarf galaxies orbiting the Milky Way, preserve in their chemical compositions a record of the first supernovae. By analyzing the relative abundances of different elements in these stellar fossils, carbon versus iron, oxygen versus magnesium, odd-numbered elements versus even-numbered elements, astronomers can work backward and infer what kind of star must have produced those elements, and by what kind of supernova they were scattered. It is forensic astronomy on a cosmic scale. The first stars are the long-dead suspects. The ancient surviving stars are the witnesses, and the chemical abundances are the evidence. The process of finding these stars is itself a fascinating challenge. Metal-poor stars are rare. For every ancient relic lurking in the Milky Way's halo, there are thousands of younger, metal-rich stars in the disk. Picking them out is like searching for a handful of ancient coins scattered across a vast beach. Large-scale spectroscopic surveys have been essential tools in this search. Projects like the Hamburg/ESO survey, the SkyMapper Southern Sky Survey in Australia, the Sloan Digital Sky Survey, and China's LAMOST survey have observed millions of stars, measuring their spectra to estimate their chemical compositions and flag the most metal-poor candidates for follow-up observation with larger telescopes. The most chemically primitive stars found so far have iron abundances that are 100,000 times lower than the Sun's, and some have been found with no detectable iron at all. These are the closest things we have to direct descendants of the first generation. One of the most famous is a star known as SM 300 and 13-6708, discovered in 2014 by a team led by Stephen Keller at the Australian National University. This star, located about 6,000 light-years from Earth in the Milky Way's halo, has an iron content so low that it is essentially undetectable, less than 1/10,000,000th of the Sun's iron abundance, but it contains significant amounts of carbon and other light elements. The chemical pattern matches what would be expected from gas enriched by a single massive first-generation star that exploded as a low-energy supernova, with most of its heavy elements falling back onto the black hole remnant, while lighter elements like carbon were expelled. It is, in a sense, the child of a population 3 star, carrying the genetic signature of its long-dead parent. Another remarkable discovery came from the Pristine Survey, a project using a special narrowband filter on the Canada-France-Hawaii telescope to efficiently identify the most metal-poor stars in the Milky Way's halo. This survey has found dozens of extremely metal-poor stars building up a statistical sample large enough to start making meaningful comparisons with theoretical predictions about the properties and death mechanisms of population 3 stars. One of the most exciting developments came in 2023, when researchers identified a star called LAMOSD Joan 1000 and 10 plus 2358. This star, found in the halo of the Milky Way, displayed a chemical abundance pattern unlike anything else observed. An unusual discrepancy between odd and even elements, combined with deficiencies in sodium and certain other elements that matched the theoretical predictions for gas enriched by apparent stability supernova from a progenitor star of approximately 260 solar masses. If confirmed, it represents some of the first direct chemical evidence that parent stability supernovae actually occurred in the early universe, validating decades of theoretical predictions about the violent deaths of the first stars. Meanwhile, the direct search for population 3 stars, or their host galaxies, continues with ever-improving tools. The James Webb Space Telescope has already revolutionized our view of the early universe in ways that even its most optimistic designers did not fully anticipate. In its first few years of operation, JWST has discovered galaxies at astonishing distances, found surprisingly massive and mature galaxies existing far earlier than models predicted, detected the spectral fingerprints of active black holes in the hearts of tiny ancient galaxies, and begun to map the topology of reionization by identifying individual ionized bubbles around early galaxies. The most distant confirmed galaxy, as of recent observations, JADE's GSC 140, is seen as it existed just 290 million years after the Big Bang. This galaxy is surprisingly large and bright, over 1,600 light-years in diameter, powered by young stars rather than a central black hole. And it challenges our understanding of how quickly galaxies could have assembled in the first few 100 million years. Its discoverer, Brant Robertson at the University of California, Santa Cruz, called it possibly the most significant extragalactic discovery with JWST to date, and noted that it extended our observational reach into the cosmic past by 40% compared to pre-JWST records. But JADE's GSC 140 is just the beginning. Hundreds of candidate galaxies have been identified at extreme distances, waiting for spectroscopic confirmation. A team at the University of Missouri, led by Heijing Yan, recently identified 300 objects in JWST infrared images that are brighter than expected candidate galaxies from the very early universe that could challenge current models of galaxy formation. The sheer abundance of bright galaxies in the first few 100 million years remains one of the biggest puzzles raised by JWST's observations. Some researchers have proposed that bursty star formation, where galaxies form stars in intense but brief episodes rather than at a steady rate, could explain the apparent overbrightness. Others have suggested that active galactic nuclei, miniature quasars, powered by rapidly growing black holes, might be boosting the luminosity of some early galaxies. Even more tantalizing, researchers have been searching for spectral signatures that could indicate the presence of population 3 stars within early galaxies. The key signature is a strong emission from ionized helium, specifically the helium-2 line at a wavelength of 1640 angstroms. Population 3 stars, with their extreme ultraviolet output, would be uniquely capable of doubly ionizing helium. And this emission line would be a smoking gun for their presence. Several candidate detections have been reported, including promising results from Xin Wang at the Chinese Academy of Sciences, and from other teams, though none have been definitively confirmed yet. The hunt is also being pursued through entirely different means. Radio telescopes are probing the 21-centimeter signal from neutral hydrogen in the early universe. This faint radio emission, produced by the spin-flip transition of hydrogen atoms, carries information about the temperature and ionization state of intergalactic gas during the dark ages and cosmic dawn. The 21-centimeter line is one of the most important signals in all of radio astronomy. It arises from a peculiar quantum mechanical property of the hydrogen atom. The proton and the electron in a hydrogen atom each have a property called spin, which can be thought of loosely as an intrinsic rotation. When the spins are aligned, pointing in the same direction, the atom has slightly more energy than when they are antialigned, pointing in opposite directions. When the atom spontaneously flips from the higher energy aligned state to the lower energy antialigned state, it emits a photon with a wavelength of 21 centimeters. It is an extraordinarily rare event for any individual atom. The average hydrogen atom will undergo this transition only once every 10 million years. But when you have the entire intergalactic medium full of neutral hydrogen, countless trillions upon trillions of atoms are undergoing this transition at any given moment, and the collective signal is detectable. The beauty of this signal is that it carries a timestamp. Because the universe is expanding, photons emitted at different cosmic times have been stretched by different amounts. A 21-centimeter photon emitted when the universe was 500 million years old has been redshifted to a much longer wavelength than one emitted when the universe was 1 billion years old. By tuning a radio telescope to different frequencies, astronomers can effectively tune in to different epochs of cosmic history, like changing the channel on a radio dial to listen to broadcasts from different eras. During the Dark Ages, before any stars existed, the 21-centimeter signal would have been determined entirely by the temperature of the gas relative to the cosmic microwave background. As the first stars turned on and began flooding the universe with ultraviolet and X-ray radiation, they heated the intergalactic gas, changing the 21-centimeter signal in ways that depended on the number, luminosity, and spectral properties of those first sources. And as reionization progressed and neutral hydrogen was destroyed, the signal would have gradually disappeared from the ionized regions, leaving only the neutral pockets to broadcast their radio whisper. By mapping how this signal changed over time, astronomers can infer when and where the first stars heated and ionized their surroundings. Projects like Hera, the hydrogen epoch of reionization array in South Africa, REACH, the radio experiment for the analysis of cosmic hydrogen, and the upcoming Square Kilometer Array, which will be the largest radio telescope ever built, are designed to detect this signal. Recent theoretical work has shown that the 21 centimeter signal is sensitive to the mass distribution of the first stars, potentially allowing astronomers to determine the typical masses of population 3 stars from 13 billion years away. The Square Kilometre Array, currently under construction with sites in both South Africa and Australia, will have a total collecting area of approximately 1 square kilometre, giving it sensitivity far beyond any existing radio telescope. When it comes online in the late 2020s and early 2030s, it is expected to produce the first detailed maps of reionization, showing the structure of ionized bubbles and neutral hydrogen filaments during the cosmic dawn with unprecedented clarity. These maps will be direct images of the era when the first stars transformed the universe, the radio equivalent of a baby picture of cosmic reionization. There's also the tantalizing possibility that the next generation of extremely large optical and infrared telescopes, including the extremely large telescope being built by the European Southern Observatory in Chile's Atacama Desert, will push our ability to detect individual population, 3 stars or small clusters of them, within the first galaxies to even greater distances. With a primary mirror 39 meters in diameter, the extremely large telescope will have roughly 10 times the light-gathering power of the current largest optical telescopes, and will be able to resolve details that are invisible to JWST. It represents our best hope for directly detecting the spectral fingerprints of the very first stellar generation. The convergence of these approaches, infrared imaging and spectroscopy with JWST, radio observations of the 21 centimeter signal, and stellar archaeology in the Milky Way, is bringing us closer than ever before to a complete picture of the cosmic dawn. We may not have found a definitive, confirmed population 3-star yet, but the evidence is accumulating, the tools are sharpening, and the net is tightening. Many astronomers believe that a confirmed detection is not a question of if, but when. When that detection comes, it will be one of the most significant achievements in the history of astronomy. It will confirm decades of theoretical predictions about the nature of the first stars. It will validate our models of early universe chemistry and dark matter halo formation. It will close one of the last major observational gaps in our understanding of cosmic history, the gap between the cosmic microwave background and the earliest observed galaxies, and it will connect us, in the most direct way possible, to the moment when the universe first learned to make light from gravity and gas. There is a deep, almost philosophical significance to the story of the first stars that extends beyond science. It speaks to something fundamental about the nature of the universe and our place within it. For hundreds of millions of years after the Big Bang, the cosmos was dark. Utterly, completely, profoundly dark. There was a matter, yes. There was energy, yes. There were dark matter halos forming, gas clouds gathering, the cosmic web taking shape in the invisible scaffolding of gravity. But there was no light, no color, no illumination, no warmth from a stellar surface. The universe existed, but in a sense, it could not be seen. It was a vast, invisible machine, running in the dark, assembling its structures in silence, waiting for something to change. And what changed, it was not some grand cosmic force, not some new law of physics, not some external intervention. It was simply gravity, doing what gravity does, pulling matter together, compressing it, heating it, until fusion ignited. The universe lit its own fires. It did not need help. It just needed time. There is something almost defiant about that. The universe was dealt a hand of hydrogen and helium and almost nothing else, a periodic table with 3 entries, and a chemistry kit that could barely make a molecule. And from those meager ingredients, using nothing more than gravity and the quantum mechanics of molecular hydrogen cooling, it built stars, stars that burned so hot and so bright that they changed the chemistry of the cosmos forever, forging the elements that the Big Bang could not, scattering them into space, enriching the gas from which new, more complex stars and eventually planets and oceans and living creatures would form. Consider the chain of events. A quantum fluctuation during inflation plants a tiny density perturbation in the primordial plasma. 380,000 years later, that perturbation is imprinted in the cosmic microwave background as a slightly warmer spot. Over the next 100 million years, dark matter in that region collapses into a halo, pulling hydrogen and helium gas into its center. Molecular hydrogen forms through a tortuous chemical pathway involving negatively charged hydrogen ions and begins to radiate away thermal energy 1 photon at a time. Over millions of years, the gas cools enough to collapse. A protostellar core forms. Fusion ignites. A star is born. That star lives for 2 million years, burning through its fuel in a frenzy of nuclear transformations. It forges carbon, oxygen, silicon, iron, and dozens of other elements in its layered core. Then it explodes, a pair-instability supernova of unimaginable violence, and scatters those elements across thousands of light years. The enriched gas mixes with pristine hydrogen. A new generation of stars forms, smaller and more numerous. Some of them form planets. On one of those planets, 4.5 billion years ago, molten rock cools and solidifies. Water condenses. Lightning crackles across a young atmosphere. In the warm, mineral-rich water near hydrothermal vents, complex molecules begin to replicate themselves. Life begins. 4 billion years of evolution later, a species arises that can build telescopes and point them at the sky and detect the cosmic microwave background, calculate the age of the universe, and simulate the formation of the first stars on supercomputers. That species, our species, is the universe looking back at its own origins. We are the cosmos trying to understand itself, and it all started with a point of light in the darkness, a ball of hydrogen collapsing under gravity, reaching 10 million degrees and igniting. The elements forged in that first star and in the billions of first-generation stars that followed became the building blocks of everything: carbon, oxygen, silicon, and iron. These elements are mixed into the interstellar medium. They were incorporated into new generations of stars. They accumulated on rocky planets. They dissolved in oceans. They assembled into molecules of increasing complexity. And eventually, on at least one small rocky world orbiting an unremarkable yellow dwarf star in the outer spiral arm of an ordinary barred spiral galaxy, those elements crossed a threshold that we still do not fully understand, and chemistry became biology. The iron in your blood was forged in the core of a massive star and scattered into space by a supernova. The calcium in your bones was created in stellar nuclear furnaces. The oxygen you are breathing was produced by nuclear fusion inside stars that lived and died billions of years before our solar system formed. The phosphorus in your DNA, the sodium in your tears, the nitrogen in the proteins of your muscles, all of it was created inside stars. You are made of star stuff, not metaphorically. Literally, every atom in your body heavier than hydrogen and helium was manufactured inside a star and dispersed by its death. And the very first batch of that star stuff was produced by population 3 stars, born in the cosmic dawn, burning for a few million years in the primordial darkness, and dying in explosions that scattered the seeds of everything to come across the voids of the early universe. There is something profoundly moving about this chain of connection. The same process that ended the cosmic dark ages, the ignition of the first stars, is the process that ultimately made your existence possible. You are linked by an unbroken chain of stellar births and deaths spanning 13 billion years to the very first fires that lit up the cosmos. We are still searching for those first fires. The James Webb Space Telescope orbits the Sun at a gravitational balance point 1.5 million kilometers from Earth. Its gold-plated beryllium mirror aimed at the farthest corners of the universe, collecting photons that have been traveling since before the Milky Way existed. Radio telescopes in remote deserts listen for the faint whisper of the 21-centimeter line, a signal from an era when the universe was young and dark and full of promise. Astronomers in observatories around the world analyze the spectra of ancient, metal-poor stars in the Milky Way's halo, looking for chemical patterns that match the predicted fingerprints of the first supernovae. We are hunting for the light that ended the longest night the universe has ever known, and we are closer to finding it than we have ever been before. The first stars burned briefly, but what they ignited has never gone out. From their light came the elements. From the elements came the planets. From the planets came the conditions for life. From life came consciousness. And from consciousness came the capacity to look up at the night sky, see the light of distant stars, and wonder where it all began. The answer begins in darkness. It begins with gas and gravity, and the slow, patient accumulation of mass in invisible dark matter halos. It begins with a fragile molecule of hydrogen, cooling a primordial cloud just enough for collapse to proceed. It begins with a core reaching 10 million degrees and hydrogen nuclei fusing for the first time since the Big Bang. It begins with fire. The first fire, the fire that shattered the eternal night and lit the universe on its long, improbable, magnificent journey to the present moment. To this moment. To the moment when you are hearing these words and looking up at a sky full of stars and knowing, for the first time in the history of the cosmos, what they are and where they came from. You have been watching. If you enjoyed this journey into the cosmic dawn and the birth of the first stars, make sure to hit that like button and subscribe to the channel so you do not miss what comes next. Leave a comment and tell us what you think. What amazed you the most, or what topic you would like us to explore in a future video. Thanks for watching, and we will see you next time.